And what we're going to do today is describe the life cycle of a star and describe the process of fusion in the sun's core. There are a lot of stars out there, and if you've ever been remotely interested in the possibilities of life elsewhere, then your question has to be tied very closely to the study of stars. Planetary systems are formed when stars are formed and eventually die as the star dies out. The chances of there being life elsewhere are tied to the number of stars, and there are a hell of a lot of stars out there. Although there's only one sun, there are, from the Earth, 500 stars that are visible to us. However, there are 400 billion in the Milky Way, and 1 times 10 to the 24 stars in the observable universe. Outside of that, we can only speculate. The life cycle of a star has some definite stages. It begins with a stellar nebula. Stellar nebulae are clouds of gas and dust, particulate nature, which is minute but in considerable and huge quantities. These clouds form the stars. They're kind of birthplaces or nurseries where stars begin to form. This is a very famous image of the Eagle Nebula, called the Pillars of Creation, and has an active star-forming region within the clouds. There are 2 general trajectories for stars, depending on their size. You could have an average-sized star, like our Sun. Our average star will eventually become a red giant in the later stages of its life as it begins to die. As that red giant begins to fade, you would end up once again with a planetary nebula. Now, planetary nebula and stellar nebula do actually cycle into each other. It's this cloud of gas and dust which is left over after the death of a star, which creates new stars. Once that planetary nebula fades, you're left with a tiny white core, which is called the white dwarf. We'll talk about each of these stages in a moment. If the stellar nebula, the cloud, forms a huge star, what we call a massive star, then in the later stages of its life, we end up not with a red giant, but with a red supergiant. That red supergiant is so unstable that the consequence of its formation is a supernova. And as a consequence of that, the supernova forms and leaves either a black hole or a neutron star. So the formation of these last 2 objects is due to the size of the star. We'll have a look at this formation and the average star life. The star spends most of its time as an average or massive star shining. So this is where our sun is at the moment. We call this a main sequence. It's in the middle of its life, and so it's stable. How does it get here, and how does it stay stable? Okay, so clouds of gas and dust consist mainly of hydrogen. Now, hydrogen particles are tiny, and gravitational effects are considerable on particles of that size. In the same way that gravity doesn't really affect us, considering our mass is so large, when we get down to the mass of a single hydrogen particle, the effect of gravity is considerable. The particles begin to attract each other to the point where they start to generate huge forces. These forces are so strong, when there's enough cloud and gas, they will actually begin to initiate a fusion nuclear reaction. Now, if you remember from topic 7, a fusion reaction is when you take small nuclei to create larger nuclei. In this case, we're taking hydrogen to generate helium. Now, as a consequence of that fusion reaction and that gravitational force inwards, we end up with 3 forces acting outwards. The first force is due to gas pressure. Now, gas pressure forces are acting outwards because the particles have huge amounts of energy Now, if you remember from topic 3 and kinetic theory, the particles vibrate, and they vibrate and collide into each other, which means that they eventually push outwards. Secondly, a huge amount of photon energy is being emitted. Now, if you can visualize or conceptualize billions of these photons flying out, that would cause a radiation pressure out. So that's your two forces that are pushing out. Your third force is something called electron degeneracy. I'll outline that in a moment on the next slide. But those three forces balance the gravitational force inwards. And what you end up with is a stable star, a main sequence star like our sun. And the photons that it is radiating due to that fusion reaction are the same photons that give us light, heat, a suntan, etc. All the sun that we need from the energies all the energy, that we need from the sun to sustain life on the earth. Now, the third pressure out, I'll mention briefly, it's called electron degeneracy pressure and is a quantum phenomena. Electrons, the electrons that are surrounding the hydrogen, cannot inhabit the same quantum state as each other. Now, quantum states aren't on the syllabus and are highly abstract, so we'll just take position as an example. Electrons and electron shells can't take up the same space as each other. So therefore there is a pressure out as these electrons refuse to inhabit the same space, right? Now there are other quantum states such as spin, etc., but pretty much it's the same idea. Because these electrons can't be in the same place and at the same time, they literally push out against each other, and that's called electron degeneracy pressure. But I won't worry too much about that. So our star spends a considerable amount of time as a main sequence star, quite happily radiating out energy for us and being nice and stable. But that story has an ending. Eventually, it becomes unstable. The first stage in that instability is the hydrogen running out in the core, in the center. When that fuel starts to run out, basically, fusion moves to the second layer. So the core is now mostly helium, but the second layer, the shell, is hydrogen. So what we get there in the second shell is a fusion reaction beginning. Now, when the fusion reaction happens here, then the rest of the star flares out to cause this kind of red giant phase. It becomes much, 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 much bigger and is red hot. The inside, however, continues with a fusion reaction because the outside core is now generating huge amounts of energy. It's even hotter in here. So inside here, we now get carbon being formed. So this time you get a fusion reaction which generates carbon, right? It's a two-step helium-helium to form beryllium, and then helium-beryllium to give you carbon, right? This is an incredibly crazy and unstable reaction. But eventually, this becomes a core, a carbon core. Now, the temperatures in a normal-sized star never get higher or high enough for the carbon to do anything useful, right? So that's pretty much the end of the story. There's a little bit more fusion to be had in the second shell. Now, eventually, when all of this is carbon, this next layer becomes a carbon-generated fusion machine. It's helium fuel out here becomes carbon. So there's like a second fusion stage in the shell. Now, when that happens, you actually get a second red giant phase. It all fans out again. But the story for this star ends with the carbon generation. Once the carbon has formed and there's no more fuel, basically that radiation pressure and that push out stops and the whole thing kind of collapses. Okay, what we end up with is fusion basically instability, and the outer layers ballooning outward and cooling. So this time it basically, they expand outwards and start to cool down and pretty much just fade into a cloud. And what you end up with is a cloud of dust again, and a central core which is absolutely tiny. This tiny little core, or carbon core, because that's pretty much what's left, is called a white dwarf. And this cloud of dust is what enabled this whole story to start in the first place, right? It's a potentially a new star. And that's the end of that story. There's a couple more videos that will go and illustrate these ideas a little bit more clearly. I don't want you to worry too much about the fusion reactions. I'm not requiring you to learn them off by heart or go into too much detail about them at this stage, okay? But I do need you to understand what the basic life cycle of a star is and how those forces balance out with each other. Tomorrow, we'll look at what happens with big stars.